All right, this is an introduction to experiment 31, spherical mirrors and lenses. Let's go ahead and share the PowerPoint. Let's see, share screen, PowerPoint. And you've had some of this already, and the reason I'm going through it is because their descriptions in the lab book is different than the descriptions in the textbook. The Survey Survey and Jewett uh, that we normally use. And so I just wanted to point out some of the differences and show you some of the things that you're going to be using for this experiment. You can see they have here spherical mirrors, what we call the principal axis, they call the optic axis. You still have the center of curvature, and you have the focal point or the focal length. The focal length is r divided by 2. It's 1/2 the radius. They talk about the vertex here. So on the inside mirrored surface, you have a concave surface, and on the outside, you have the convex surface. So these are some of the points that we'll be talking about. The the On the concave surface, we've shown that um, I've got some demonstrations previous to this that show that the incoming light rays converge and meet at the focal point, and you get an image at the focal point. On a convex surface, the rays come and they just diverge. They won't converge, and we'll see that in the experiment. So this is some ray tracing. It is the same. This is for a concave mirror. It is the same as they've given you in the textbook. Uh, but there are some things I want to point out. What they call D object is what the textbook calls P, and the DI is what the image distance is what the textbook calls Q. So you'll see instead of P, you'll see DO, and instead of Q, you'll see DI in some of the equations. And that this is it for a concave mirror. Here it is for a convex mirror, and this is the ray tracing. The I've color coded it to kind of help you. The We've got 3 different rays that we do to construct, and it's the intersection of all these rays that will determine where our image is. If you look at the right-hand side of this image, you'll see that it's a little bit different than I had to modify it because I think they did it. The textbook did it incorrectly. Number 1, we have the chief ray. These are done in different order than the textbook. I kind of like their order a little bit better. I've color coded it. So the red is the chief ray. Chief goes through the center. So C for chief, C for center. You can remember they both start with C. So the chief ray goes from the top of the object through the center, hits the mirror, and returns. It's a single ray. It doubles back on itself, so it just looks like one ray. So there it is for concave. For the convex, you can see it goes past the top, through the center, and back. So that's the chief ray. A chief ray from the object goes through the center of curvature C and is reflected back through C. Now, I mean, it's all points on the object, but it's just easy to pick the top. It also helps you get the magnification. Now, the next one is parallel to the focal point. So from the top of the object, this is the green. Notice that it's parallel to the principal axis. The green goes parallel to the principal axis, reflects off the mirror, and goes through the focal point. So it's parallel to the focal point. You can see it here. Oh, I forgot to highlight the green here. I'm not going to go back and change it, but uh, the green bounces here, and the green comes here and bounces off the mirror. But if you backtrack the dashed line from this, what should have been green, you'll see it goes through the focal point. And then the last line is the focal point from the object through the focal point, and it comes out parallel. So here's the top of the object. This is the blue. Top of the object through the focal point, hits the mirror, and comes back parallel. Let's do it for the uh, convex, the diverging mirror. It's top of the object through the focal point. You can see that the ray doesn't uh, it goes through the focal point on the image side, but is reflected at the surface here, and it comes back parallel. So you have chief through the center, parallel to the focal point to parallel. And those are the three rays that we use to construct an image, where the image goes. Okay, these are some of the equations. You're familiar with this equation, but the way you were seeing it was 1 over P plus 1 over Q equals 1 over F. Well, most of the time we want to find the image distance. And so DI is equal to 1 over, you just do the simple algebra, 1 over F minus 1 over D0. Well, we get a common denominator, D0F. And when we get down to the bottom, you can see that the image distance is equal to the object distance times the focal length divided by the object distance minus the focal length. Okay, let's, this is table 31.3 in your experiment. It's similar to the table that was given in chapter 35 for the sign convention for spherical mirrors. So it's the same. You can check it out. I'm not going to spend much time on it. Here are some lenses. The biconvex lens is a converging lens. You can see all the lines come and they go through the focal point on the other side. There's a focal point on one side. You know, here's a curvature of radius, so the C is probably over here, and there's probably a C over here, but you get a focal length on either side. Now, they don't have to be the same. I think for our experiment, they are the same. And this is it for a divergent lens, a biconcave lens. I don't have one of those, so when it comes to using a biconcave lens, we'll skip that part of the experiment. And this is the ray tracing for lenses. You can see the chief ray goes right through the center of the lens. The parallel through the focal point, and then focal point parallel. So we have the same construction, the same three rays that we had. This is it for a diverging lens. The principal, here's the object through the center of the lens. The parallel through the focal point. That's you can see that this, if you backtrack this number 2, it goes through the focal point on this side, and then 3 is the focal point, and it comes out parallel. But you can see the parallel is here. But you can see that if you were to trace it down here, it would go through the focal point. Okay, here's the Lensmakers equation. 1 over F is equal to n minus 1, where n is the index of refraction from the lens material. Again, the radii don't have to be the same, so R1 can be different from R2. When they are different, in general, F does not equal to the radius divided by 2. However, if the image distance equals the object distance, then the object distance is equal to twice the focal length. And that's it for the intro. We'll get on with the experiment.